Better Buildings for Humans is powered by Advanced Glazings, makers of the Solera line of products. Solera is the leading glass glazing made specifically for architectural daylighting and with extreme insulation performance. Learn more at advancedglazings.com.
Hello and welcome to this week's episode of Better Buildings for Humans. I'm your host, Joe Menchefski. This is the podcast where we explore the impact that the built environment has on our health, our wellness, our productivity, our general joy of being alive. And of course, we always have to talk about sustainability as well. Today, I have Peter Pescatore from Cabot Carbon in the greater Boston area. Advanced Glazings has been working with Cabot for a long time now, close relationship, to integrate their Aerogel material into our glazings. And today we're going to talk about Aerogel. We're going to go on a little bit of a deeper dive with Peter and learn a little bit more about the magic of Aerogel. A lot of you have heard about it, so I want to make sure that everybody understands it. So Peter, welcome to the show.
Well, thank you very much for having me, Joe.
Now, it's a pleasure. Let's start by allowing our guests to learn a little bit about you. Tell us about your career and with emphasis on the path that led you to Cabot and the Aerogel division.
Sure. So I have a master's degree in mechanical engineering with a focus on heat transfer from Northeastern University. And then I spent roughly my first 20 years of my career working in the appliance industry, doing product design for cooktops and ranges and ovens and water heaters and furnaces and so on. And in the course of that work, certainly did a lot associated with trying to improve the efficiency of those various products. And I'd say somewhere around 2005 or thereabouts, I first came in contact with this, what seemed like magical material, this frozen smoke, as some people call it, the aerogel material, particulate aerogel particles. And I was on a project where we were trying to utilize them. It turned out it didn't work for what we were trying to do, but it was a very interesting material. And I dug a little deeper into it. And then a year or so, or 2 years after that, learned of a job opportunity at Cabot Aerogel. It's, that was probably 2008 time period, and started at Cabot in the summer of 2008. And have been within the Cabot Aerogel business ever since. The first part of that was what we call applications development, which is working primarily with customers for how they could take this unique material and integrate it into their own products. And specifically, actually, I started in the daylighting area, so it definitely overlaps with advanced glazings and the work that was going on, in that time period to try to use aerogel particles for efficiency. And over time, the role has expanded a bit, and now I have global commercial responsibility for Cabot's Aerogel business.
All right. And it truly is magical. That's the right word. Or at least if you're standing looking from the outside and you understand the properties of the material, it does seem like it really is magical. I can't imagine going any further in this conversation without helping people to understand what aerogel is. So, Peter, can you explain ultimately what it is?
Sure, Joe. So first of all, I should start off by saying aerogel is somewhat of a generic term, and it really is a reference to a material with a certain structure with very high porosity, very lightweight. And aerogels have been around almost 100 years. The original work in developing an aerogel process was done by an MIT professor, Stephen Kistler. And as I understand it, I don't know if it's lore or not, but as I understand it, it was some type of a bet that he had with a colleague challenging him to replace a liquid inside of a gel of a jelly, I guess they called it at the time, with a gas. He was successful. He patented a process. And that's kind of the core idea of aerogel. But then within aerogel, there are a number of different materials that can be used as the basis to create that structure. So there are companies that have carbon aerogels, polyimide aerogels, polyurethane aerogels. But the most prevalent one, and which is what Cabot does, is a silica aerogel. And then within just saying silica aerogel, there are a number of different processes. So there are many companies out there that make silica aerogel blankets where they start with, say, a fiber-based product, perhaps a ceramic fiber or a gas fiber, and they go through the aerogel gelation phase of particles being attached or embedded into those fibers, and then they sell an insulating blanket that's quite efficient and does a lot of tremendous things. In the case of Cabot, we don't have a fiber-based product. We make aerogel particles, so these are granular-based materials. But generally speaking, the aerogel itself is similar to what you'd find for the aerogel particles within those blanket materials. What's different is, so when you make aerogel and when you want to drive the solvent out of the pores of that structure, there are a couple of different ways to accommodate that or to achieve that. Many companies use what's called a supercritical approach, where they use high temperature and high pressure, often in a carbon dioxide or CO2 environment, to do that exchange to extract the solvent out of the pores of that structure. But for Cabot, so in those supercritical systems, they tend to be what I would refer to as like a batch process, right? Where they'll make a certain amount of material and then have to put it in a kiln to drive or expose it to those conditions to drive the solvent out of the pores. In the case of Cabot, we have what's referred to as an ambient process. So while we're still using temperature, we're not using pressure. It's done at ambient pressure in an oven in a nitrogen environment where we are at a slower rate driving that solvent out of the pore structure of the aerogel, and done in a way that you do it slow enough so you don't collapse the structure. Because if you collapse the structure, then what's left behind is just silica particles in your silica provider and not really providing the insulation that's associated with it. So I don't know how detailed you'd like to get in, but we talk a lot about structure. The reason why silica aerogels perform the way they do is because of their pore size. And the pore size in most silica aerogels are somewhere between, say, 10 and 50 nanometers. And I know for me, anytime I hear a really big number or a really small number, I kind of need something to try to help me, put it into some meaning in the real world, we'll call it, right? So when you hear a giant number like a federal deficit that's in trillions of dollars, you got to think about how many zeros are involved. And when you hear a tiny number like nanometers, you have to think about how many zeros are involved after the decimal place before you get to where the numbers are. And a nanometer is 1/100000th of a meter, which again still is hard to comprehend. So people can think about a meter, and in the US it's about 3 feet, right? And then a millimeter being 1,000th of that, which is about the thickness of your credit card. Go 1,000th the thickness of that, you're at a micron, which something people might think about would be maybe a human hair, which, I mean, they vary, of course, between, say, 20 and 180 microns, but they're on average around 80. And now you got to go more than 3 magnitudes smaller than that to get to the size of the pores of these aerogel particles. So we're talking about something that is, almost infinitesimally small. And what that does is it gets so small that it's smaller than what's referred to as the mean free path of air, which is generally speaking the typical distance between air molecules before a collision. And the simplest way we describe the product to people is it's almost like aerogels creating tiny little jail cells for these air molecules in such a way that they can't interact with one another. And therefore, when there's a heat source, say it doesn't have to be a flame, it could just be a temperature difference. When those air molecules get excited and start moving around more, there's no opportunity for them to collide or interact with other air molecules and transfer their energy. And that results in very low gas phase thermal conductivity, lower than even still air. So when you think about traditional insulation forms, say fiberglass or mineral wool, they're requiring or relying on air being trapped between fibers, or polyurethane foam might be air trapped inside the cells. And that still air is what's giving those products their thermal performance. But the reality is air is never really still. If there's a heat source, the molecules will move around. And if they can interact with one another, they'll transfer energy. So silica aerogels, because they trap those molecules, can get you 2 to say 4 times better thermal performance than those traditional insulation forms. So that's a little bit about aerogel, its structure. And in the case of Cabot, we make it in a continuous way in a granular form. And the particles are big compared to the pore sizes. So we may make material, as you are familiar through advanced glazings, that's 1 to 3 millimeters in size. So again, thicker, bigger than the thickness of that credit card. And you can take that particle and break it, and you'll never get down to a point where you've broken it down to its pore size.
Right. Now, what about light transmittance? How does it still manage to transmit light, which is an amazing property of such a highly insulating material?
Yeah, so one thing I should point out in general about silica aerogels is, currently at the scale that we produce at, they're fairly expensive. So even though they're 2 to 4 times better from an insulation point of view, they may be 10 times more expensive from a cost point of view. So typically, in order to justify using the particles, you need a secondary benefit. And in advanced glazing's case, that's light transmission. And what's happening there is as the light enters into this structure, so think of the silica particle with its three-dimensional structure. It's got these chains of very small individual silica components that might be on the order of 5 nanometers. But then these pore sizes, light will enter into that space of that pore and then will be scattered in a way that one will allow, it's translucent, not transparent, but it will allow for a lot of light to pass through, but it'll do it in a way that's very different than many other materials. So you figure a typical window, a clear window with the sun shining through, you have a shaft of light that's coming into your space, right? So you get a lot of light where the sun comes through, and then a big contrast between that space and the space, outside of that shaft of light, and it can cause issues with glare and things like that. So with the aerogel particles, they act more as a diffuser. So as the light enters into them, into each of these individual particles, they're all scattering in a bunch of different directions. So that light gets through it, but gets spread. It gets deeper into your space, gets wider into your space. So you get less contrast, which is the big benefit there. So you have this thermal benefit, you have this light transmission benefit, again, translucent, not clear, but translucent. And the light being spread deeper into space kind of gives a much more pleasant atmosphere. So that's generally how the value proposition there.
Yeah, it's a nice soft light, and a lot of it gets redirected upwards in the walls and the ceilings, so it stays in the visible light spectrum and yeah, continues in its journey into the depth of the building. So you end up daylighting a much larger floor area. It was certainly, part of what attracted us to it, that it was that combination of the diffused light and the high levels of insulation. Can we take a little bit of a side trip? At the very beginning, you mentioned, carbon aerogels and polyurethane aerogels. How different are the properties with, say, a carbon aerogel?
So the carbon aerogel tends to not be as good of a thermal insulation performer. It's doing other things. Often it's either being used to capture inside of it other materials or to act as a filter in some way. And that's primarily because the base material, being carbon, has a higher thermal conductivity than the base material of silica. So again,
Right.
the silica aerogels, it's not just the pore structure, it's the fact that the individual components that make up that structure are also decent insulators, as opposed to if you made it out of a carbon, which has a higher thermal conductivity, you don't get that performance. But carbon aerogels do a lot of other tremendous things, just not in the realm of insulation.
Right. So with each base material, there's a pretty consequential, performance parameter difference.
That's right. And sometimes some of those materials, it can be a little more challenging to get down to that pore size range where you're really below the mean free path of the air molecules, and that can also have an impact on that thermal performance.
Short lifespan single use plastic glazing is not a sustainable solution for daylighting. Solera is the glass based alternative for the new millennium. Learn more at advancedglazings.com.
Okay, I really like that. So, we had a pretty good conversation about why it's such a valuable product in insulation and in glazing, I mean, specifically, right? Extremely high levels of insulation, but also allows the light to pass through and creates this ideal situation of a nice soft diffused light. What else is aerogel used for in construction, Peter?
So outside of glazing, the biggest application in construction that we see for aerogel particles is primarily in Europe, where it is used as an additive into spray applied plaster systems. So something we would kind of consider as stucco type materials in North America, I think. So if you think of your stereotypical, say, 400 or 500-year-old German, Swiss, France, Austria type home, they have a certain look to them, right? Where you have the timber framing, and between the timber framing is this stucco-like material that you see from the outside that looks, very appropriate to the time period. Those are typically lime-based plaster systems that have been around for 4, 5, 600 years. They're used as an insulation material in those historical homes, but the straight line-based plaster is not a very good insulator. It's okay, right? So as these countries are requiring additional energy efficiency with regards to the homes, people who are, or I should say homes, not just homes, homes and businesses and municipal buildings, people who are looking for alternatives now to insulate those buildings, but to keep that historical look, are looking now towards aerogel-based plasters. And there you get maybe 3 to 4 times the insulation performance of straight line plaster, but the same look. So if you take a historical building, remove the old line-based plaster, apply this new line-based plaster with aerogel, you almost can't tell the difference. So it meets the historical commission requirements of maintaining the look of those buildings with 3 times the efficiency. So that's actually the biggest market that we see today in building and construction for aerogel particles.
So is that all just new construction, Peter, or can you go on top of the plaster that's there to add another level of insulation performance?
Yeah, it's primarily renovation. So if you're renovating a historical home, you have the historical commission and the requirements that are put in place by the historical commissions in the various communities. So this is one way to meet those requirements in a renovation to keep the look and feel of that 400 or 500-year-old building and get higher energy efficiency.
Really cool. Exterior or interior or either?
Primarily exterior. It can be done in both cases, but it's primarily applied an exterior spray applied system.
Really cool. What do the Germans call it? Volkwerk, I think, is the style with the structure sort of exposed, but the plaster is in between.
I honestly don't know the German word for it.
I think that's what they call it. All right, let's talk, I guess, economics a little bit. Okay, so there's a bit of a balancing act in the world of buildings, and that's the classic between the initial costs and the ongoing savings, capital versus operating. But there's also a balancing act between the cost of something versus market size, right? And if you can drive the cost down, that gives you access to broader markets. Are we seeing an overall trend towards lower costs in the manufacture of aerogel?
I think we are, and it's being driven by something that has nothing to do necessarily with energy efficiency. There is an emerging market that many are describing as finally the big global market that aerogel manufacturers have been waiting for. And that is insulating the battery cells in electric vehicle battery systems.
Oh, I've heard about this.
So there is a small risk of a cell in a battery, electric vehicle battery, lithium-ion battery, getting into what's called a thermal runaway. And in the case of that, if a single cell goes into a thermal runaway, it's not typically a big deal, other than you have to replace it. But if that starts to now affect its neighbors because it gets into a thermal runaway, and that thermal runaway could be caused by a mechanical issue, it could be something that comes up from the road, you run over a board with a nail in it, punctures the battery, you now get the materials of your anode and cathode interacting with one another in a way that they're not supposed to. That creates this uncontrolled or temperature rise. And in a single cell, like I said, it's not necessarily a risk, but it's getting back to thinking about that old TV commercial where if it tells 2 friends who tell 2 friends who tell 2 friends, right? So if that one cell gets into a thermal runaway, affects its neighbors, the neighbors affect their neighbors, and so on, you now have a fire. And you have risk to the occupants, and a case where it's really difficult for the fire department to put out the fire, and a whole bunch of issues associated with it. So the automakers and battery makers have looked at that and said, well, one solution is if we can insulate around our battery cells, we can limit the risk of one cell, if it goes in a runaway, telling its neighbors that it's gone into a runaway condition, right? But of course, the real estate in a battery is expensive. You want to use as much battery in that space as possible to get the range for the vehicle. You don't want to put a bunch of insulation. So what's a good material to use that could be really thin, that provides high performance? It's aerogel or silica aerogel based solutions. And whether that be a blanket form or a film or whatever. So the last 2 years, there's been tremendous growth in that marketplace of using silica aerogel based solutions to insulate the battery cells. And as we see more and more electric vehicles get made, more and more of the automakers are going towards these type of solutions of using silica aerogel solutions as insulation. And their demand for material is much larger than any market we've seen to this point. So when we think about, well, how do you take the cost of aerogel down? It's scale. When you have a process like Cabot's that's produced in a continuous way, if you could just build a plant that's 5 times the size or 10 times the size, your cost structure will be dramatically better. But the cost to build a plant 5 or 10 times the size is many tens, if not hundreds of millions of dollars. So you really need a market. So it's always been this chicken and egg thing of,
Yeah.
wow, if the price was lower, more people would use aerogel. And if more people use aerogel, we could get the price lower. And it looks like the EV market might be the big opportunity that all silica aerogel manufacturers have been waiting for to get to the right scale.
That is fantastic news. So it becomes like the heavy water in a nuclear power plant to control the reaction rate.
In a way, yes.
Only it's not the ongoing scenario. It's more of an emergency scenario.
Yeah.
Okay. Oh, that's brilliant. And that makes me really happy. That's just wonderful news. I knew there was a connection. I didn't know what it was. So I'm glad to hear that. All right, let's talk about lifespan. How long does aerogel last? Let's assume it's in a closed scenario, like in Solera or, well, battery application, anything where it's, not exposed.
Yep. Yeah. So one of the things that is an added benefit to silica-based aerogel systems is they're quite inert, right? So whether it be Cabot's aerogel or, the blanket manufacturers or whatever, in order to cause damage to that material to lose its insulation form, it takes a lot. And typically it would take exposure to something like a solvent in order for there to be, because the particles themselves are hydrophobic. So even if they're exposed to water, they're not going to pick up water and lose their performance, unlike other fiber-based insulation systems where if you have fiberglass in the walls of your home and somehow there's a leak in that space and the fiberglass gets wet, it will never be an insulator again because the fiber structure, not only is there water present, but the fiber structure has changed. And because of that, you lose the air space between the fibers, which is what those insulations rely on for their performance. So in the case of silica aerogel, the water has no impact on it. It's UV stable. So we've been producing aerogel particles for 23 years now, and stuff that's 23 years old performs exactly as it did 23 years ago. So we see no change in its thermal performance. So from a life cycle or life performance point of view, it's very robust.
Yeah, which is brilliant when you're talking about embodied carbon and those sorts of things. So if you put it in, it lasts, the lifetime of the building and then some. So that's wonderful news. We've kind of asked this question already, but I wanted to do it in the context of buildings. You talked about aerogel as being, the thermal barrier that can reduce the risk of overheating in EV batteries. Where does it stand with regards to fire performance in a building?
So again, the particles are silica-based. The silica is not flammable. There is that hydrophobicity does come from a surface treatment that's on the surface of the particles, but it's in a low enough concentration that it doesn't really, it by itself won't burn. It may add a few calories into the system, but they're minimal. So it's really good from a fire performance, which is why in those battery systems, they're using silica-based aerogel solutions, because if a single cell gets into a condition of 1,000 degrees C or something like that, not only does it insulate it, but it doesn't catch fire, those conditions. So it's a really good fire insulator material.
Yeah, I kind of knew the answer, but I really wanted to make sure we talked about it in the context of buildings as well. Is anybody using it in that, like specifically as a fire retardant, or does that make any sense at all from an economic?
People have tried, one of the limitations, I should say, though, is that silica will, I don't remember the exact temperature, but silica will eventually melt at a high enough temperature. So depending on the type of fire you're trying to protect against, it might not work in that application just because the temperature is too high. I know that there was work done to integrate it into some of these intumescent coatings and things like that in an effort to improve the insulation performance and maybe provide some additional backbone for fire resistance, but the results from that have been mixed. So typically just as a pure fire preventer, we don't see it being used a lot, but some of the blanket materials I think do find their use because they have to pass these jet fire tests and things like that. So again, from a particle point of view, we're selling particles to someone else who's making a form typically, and it's possible that those forms might find their way into that market, but it's not a big market that we can see.
Understood. Okay. The circular economy, lots of conversation about that these days, and rightly so. What happens to aerogel at the end of its life?
So a lot of it depends on how it's being used. So if we take the case of the Solera product from Advanced Glazings, right? So what Advanced Glazings does, for those that don't know, is the silica aerogel is put into a honeycomb structure to kind of hold the particles in place so that the glass in the window system can expand and contract with temperature differences. The aerogel particles stay where they're supposed to stay. In an instance like that, as long as you're able to remove that product from the final window, you could certainly reuse those aerogel particles in the next generation of a window system, because nothing in that system is going to have an impact on their performance. Now, in the formulated solutions like coatings and things like that, now it's a little harder because it's kind of embedded with a whole bunch of other materials as part of a fully formulated product, and how one could get the aerogel particles out of that formulation, I don't know that there's any easy solutions to that type of thing.
Gotcha. So focusing on Solera for a second, if it ended up in a landfill for some reason, that the time wasn't taken to dispose of it properly and it ended up in a landfill, it's made of silica, so there's no opportunity for harm there from how I see it. Is that correct?
I mean, that's correct, except that, given the cost of the material in there, I would certainly encourage people to try to recover and recycle it, but it's not going to cause harm if it's disposed of in that way.
Gotcha. Okay. Yeah, brilliant. All right. So what lies ahead for aerogel? Like, what are your big plans for performance improvements or, broadening applications? You did mention the EV and we spoke about that, but outside of that, is there anything that you're doing to broaden applications or improve performance in current applications?
Yeah, so for us, I think what we see in addition to that EV space is a lot more of these formulation providers using aerogel as a particles as a building block. So we're seeing a lot more in the area of insulative coatings. So these would be, unlike the plaster system that might go on fairly thick on the exterior of a building, these are typically spray applied coatings that go on 1 or 2 millimeters thick to solve a specific need. And one thing I did miss when you asked the building construction market is that one area in building construction that has, especially in North America, is you have a lot of apartment houses being built steel frame with steel frame balconies, and you have this steel to steel connection of this essentially fin hanging outside of a building that is either bringing in the heat in the summer or losing the warmth of the inside to the exterior in the winter. So we see a lot of companies trying to develop spray applied coatings that could go directly onto steel beams at the interface between the balcony and the building, for example, to reduce energy loss, but also it helps to reduce the risk of condensation. So you kind of can get a scenario inside the wall where you get the right temperature humidity combination because of your steel beam being a different temperature than its surroundings, where you might get the water condensing onto the surface of the beam inside your wall, causing mold and mildew and issues like that you don't even know about until you have a big problem. So we see a number of traditional paint manufacturers who are looking to create these high performance coatings, both for that more residential architectural space in these apartment buildings, but also into spaces like insulating large tanks or process vessels, or insulating ovens in a very steamy food environment or something like that, where you can't use traditional insulation forms because of the presence of the water or the steam or the environment, but you can use an aerogel solution because of its hydrophobicity. And while I don't think any of those markets will approach the size of the potential of the EV market, these are all complementary markets that allow us to think about a different scale of manufacturing. And really we see that as the big opportunity in silica aerogel is scale.
Oh, that's really exciting. And the thing about the balconies is really cool too. I had a guest on our early days that talked about balconies as being a very significant source of heat loss. But, there's a balancing act there because the balcony brings health and brings joy to the people in the apartment. So, it's very valuable to us. And this could eliminate the trade-off, or at least absolutely minimize the trade-off. So
that's true, because a lot of the existing solutions involve cutting the beam, putting a thermal brake pad or something like in there. So now you've added complexity and you've limited the mechanical strength of your system so you can only have certain size. This spray applied system, you leave the mechanical structure exactly the way it is, and it's about having insulation in the right places.
Do you want to bring lots of healthy, beautiful natural light in your building and still meet energy codes? Try Solera from Advanced Glazings. Learn more at advancedglazings.com.
Oh, I love it. Okay, Peter, we've come to the part in the show where I ask the $1 million question. So this is a question I ask of every single guest. And I know your world is a little more diverse beyond buildings, but I'm going to ask anyway, and you can answer from whatever perspective you'd like. What makes a great building?
From my perspective, so I've listened to a number of your podcasts, and I know that a lot of people have come up with some really creative answers to this. So I doubt that I'll come up with something that hasn't been said before. But for me, I think a building has to be welcoming, and by welcoming, I mean a number of different things. Right? So one part of that is there's a physical attractiveness to it, right? So that it fits within its environment. So if you see a building that just doesn't seem right in the space that it's in, it's not inviting and sort of not encouraging you to come into it. So I think buildings that integrate themselves well with their surrounding space, for me, is an example of welcoming. And then once you're in the building, certainly comfort is important. And I think this is where insulation comes into play and can play a big role in that type of a system. So if you're in the center of the building feeling a certain way, as opposed to when you're near a window feeling a different way because of either how the HVAC system is working or how well or how poorly the building might be insulated and how that feels, and then integrating that space with its outside environment. I know there's a lot of statistics out there about we spend so much time indoors, right? And we're not really, from our evolution, supposed to be spending this much time indoors. We've lost our connection to the outside world. So I think where buildings can help us is help with that connection. Simply through daylighting, absolutely is one place that can be. But again, just integrating, for me, it's like integrating that building space with its surroundings that encourages you to use the building when you need it, but also encourages you to go outside of the building when the opportunity presents. Not when it's the middle of the winter necessarily, but when the weather allows for that.
Oh, fantastic. I love it. All right, Peter, is there any news that you'd like to share, anything you'd like to promote that we haven't covered already?
No, I don't think so, Joe. I think I, kind of come back to that same point of, for me, I first got attracted to the aerogel particles because it's a really interesting product and it does things that really nothing else that we can see out there can do. But the big key now is how do we get to that scale? How do we get it into enough marketplaces so that it brings the cost down and then therefore will build on itself and be used in more and more places. So I think it's thinking about a future of a larger scale of aerogel type production plants.
No, fantastic. Well, I'm doing my best, Peter, I swear. Trying to get as much Solera and Solera wall and creating beautifully connected buildings as I possibly can. Peter Pescatore, thank you so much for your time today.
All right. Thank you very much, Joe.
Take care.
Okay. Bye.
We hope you enjoyed this episode of Better Buildings for Humans. For more information on the world's best light diffusing and highly insulating glass glazing, please visit advancedglazings.com.